Hey all, Luis Casas asked me to go over some problems, and I don't have the handout I gave you a while back, so I came up with a different one. And so let's go over step by step. Don't forget to do and review your homework problems and also the handout that I gave you previously. And if you have any question, you just ask me over the weekend. Um, so let's initiate with this problem. We have an electron. So the magnetic force is one that is given by the cross product between V and B. And to operate and to figure the direction of this cross product, you must use your right hand rule. You place your fingers in the direction of first vector, bend them towards the second vector, and that gives you, your thumb in fact gives the direction of the cross product, this product over here. Now then you have to look at the charge. If the charge is positive, the direction of the force is the direction of the cross product. Otherwise, you have to reverse. So we have a negative sign applying um, to this cross product that gives the direction of magnetic force. So let's see how that works. We have an electron moving west, so let's make a direction. So when you do the Cartesian orientation, north is up, east is to the right, and south is to the bottom part, and west is to the left. And also we have upward and downward. So upward is some direction that goes towards you as you look at this drawing, right? Something like this. And downward is a direction that goes to the floor. So don't get confused with that. So imagine you are standing up and then you look towards north. So you look in a direction that is parallel to the floor. And your east is in a direction that is, if you are facing north, is in a direction to your right hand side, parallel to the floor. West is left hand side, if you are facing north, parallel to the floor. Now, so downward means towards your toes, towards your foot, and upward is towards the sky. Okay, so you have an electron that is moving west, so it's going in this direction here. This is electron. Electron is a negative charge, by the way. And so if it is moving in that direction, it necessarily means the velocity vector is given, right? So if you think about this cross product, one of the quantities is given. In fact, two, because electron has a negative charge. Don't forget this negative is very important. So the direction of the velocity vector is given, and because of this field, the electron curves upward. Oh, so the electron curves upward, which means the magnetic force is going towards you. So the magnetic force goes towards you. And that's why the electron, let's say, let me do this drawing a different orientation here. Let's say this is north, this is south, this is east and west, over there. So the electron goes like this, right? Imagine this is parallel to the floor and the electron curves upward because at that moment there is a magnetic force like this sticking up, right? Perpendicular to, like levitates and lift up the electron at that point. So we know the direction of V. The direction of V is here, right? Towards west. And we want to know which direction the magnetic field is. So basically, the field should be one that provides a cross product between V and B that is downward. So you want a V cross V be downward because of this negative charge that will flip this direction, giving therefore the direction of magnetic force. So which field that should be? So if the field is north, that should give the trick, right? If you make a field that goes north, place your four fingers towards the vector V, and then bend them towards B with your right hand. Your thumb ended up being pointing down, but you need to flip because the charge is negative. So north is the answer. A proton moving west is the same idea. So let's do this. It's north, east, west, and south. And then we have the up, up, and we have the down direction. Okay, a proton is a positive charge. So a proton has a charge that is positive. So you are looking to determine the direction of a cross product in this case, because the charge will not changing. The charge will not flip the direction of cross product. So the direction of cross product is the direction of magnetic force. So proton moves west. So velocity vectors are there. And enters a magnetic field. Because of this field, the proton curves upward. So magnetic force is like this, which means V cross B. So B has to be like this, right? V cross with B gives a magnetic force that is upward. So towards south, that's what it is. Let's do another one. You have three particles that travel through a region in space where the magnetic field is out of the page. That's the definition of out of, or the symbol of out of page, showing the figures what are the signs of the charge of these three particles. Now, particle number one, so look at this. Particle number one, the magnetic force is like this. And the particle number two, the magnetic force is like this. And particle number two, the magnetic force is none. Right? There is no magnetic, there is no force because the particle does not change. So basically, since magnetic force, so let's look at the particle 2 only. It's Q V cross B, right? So the magnetic field is out of page. V is like this. This is the direction of V here, right? And B is out of page, which means the charge is none. So Q is equal to 0 because there is no force, right? We have to nullify this quantity here. So the net force here is 0, so the magnetic force is 0. But in the particle number 3, see the direction in which particle goes like that. So V is like this. So B is up. Therefore, the charge here must be positive. And charge number 1, so you put a velocity vector like this. V cross B is towards V cross B in 1. So V cross B for the particle 1 is opposite to the direction of FM. So just do it your right hand. So take your 4 fingers, put along the direction of V, bend towards a vector that comes out of the screen towards your face. So your thumb is pointing downward towards your right hand side, and that is opposed to the magnetic force. So which means the charge must be negative. So Q1 must be less than 0. Okay, so let's do this one over here. So when you have a particle going in a circle, you have a magnetic force, and that happened to be also the centripetal force. So let's review physics 2A. Centripetal force is mv squared over r, and this centripetal force happen to be your magnetic force, which is QVB. Right? So we have some basic equation, which is mv, which is also momentum, is QRB. So this is basically in this type of problem. So you can start up that way. So you have a proton is a positive charge moving in, oh, by the way, and also the circle, the circumference is equal to 2 pi r. R is the radius, right? And the average speed in this case is the circumference, the path divided by the time, because I'm seeing the time over here. Moves in a circle perpendicular to the field. It takes time t for each circle. So which means you can derive from here. You can derive from here an equation that has v and has the time. So that's the period. Now, if the proton speed is triple, what would now be its time to go around the circle? So if we go to a new velocity that is 3 times as the previous one. So if you look at this first equation here, m v prime is equal q r prime b. And then we can write v prime as a function of v. And then we can have r prime. So the new radius when you triple 3 mv divided by qb. So the new radius is going to be, in fact, if you look at it's going to be 3 times as big. If you increase the speed, the radius is going to be 3 times as big. Now, and we want to find the time. What would be the new time? So the new time can be derived from here, right? So the new time is going to be v prime, which is the new speed, which is 3 times as the previous one, divided by 2 pi r prime. And then you can write your new time is going to be 3v divided by 2 pi r prime, which is 3 mv divided by qb. So cut. This is qb divided by 2 pi m. Huh. What does that give me? So the new velocity is equal to 2 pi, the new radius divided by the new time. So the new time is equal to 2 pi r prime divided by v prime. So this I know. So can I need to write, okay, so the time, this is 2 pi r prime divided by v prime, which is 3v. Okay, and v is equal, to pi r divided by t. Okay, so now 2 pi cancel, and oh, but that's interesting. Then the radius, as we saw, is 3 times as the previous radius, right? Is 3r divided by 3r. So this radius here, the new radius, is 3 times as big as the previous radius, and then that's what I replace it here. And then we find the time is the same. Time doesn't change. So let's move here. It's too confusing. The magnetic field at a distance 2 centimeters from the long wire. Okay, so now we have a new equation here. This is the equation of a magnetic field. Now we have a different situation, and that is you have a current carrying wire, right? And because of this wire moving around, it creates a magnetic field around itself. And the magnetic field is given by, again, a right-hand rule. What you do, you place your thumb, you rest your thumb on the wire like this, and then you curl your fingers as if you were going to grab the wire, and by doing so, you figure the field circulates like that. So right here it should go like that, and here it should go like that. Okay, so again, it's the right-hand rule. So it is said the magnetic, and by the way, the field for a long wire is equal to mu naught. It's a constant I divided by 2 pi d. D is the distance from the point where you are attempting to calculate the field towards the wire. So it is said the magnetic field at distance 2 centimeters. So please convert 2 centimeters. Distance is 2 centimeters. Convert that to meters. It's 4 micro Tesla. So 4 micro Tesla is the field, is equal mu naught, is a constant, times the current divided by 2 pi times the distance. And then with that information, we can figure the current. So current can be calculated. I'm not going to calculate that. What is the magnetic field at distance 1 centimeter, right? So a half centimeter. So at a distance 1 centimeter, well, in fact, the field is going to be twice as big. You can figure here, right? So the new field is going to be mu naught current you just calculated divided by 2 pi d over 2, right? So you are reducing. So the field is going to be 2 times as big. Yeah, it's the same idea here. If you can't do, let me know. That's the same idea. Let me know if you can do. Okay, so you have 2 long parallel wires carrying current 20 amps and 5 amps in opposite direction. So let's say you have a wire that's kind of coming out of the screen, current 20 amps, and you have another one that goes opposite to that, current 5 amps. The wires are separated by 20 centimeters. What is the strength of the magnetic field midway between the 2 wires? So somewhere here. So strength means we just want the number associated with the field and not the direction. But let's try to get the direction too. So how do we figure that? So according to this drawing over here, let's take this current and make it red. Make it red. So the field of this current, so how do? We take our thumb in the right hand, the thumb put on the wire in the direction the current flow. So when you turn around your 4 fingers as if you are going to grab the wire, you figure the field at this point is like this, B20. Okay, and let's look at the 5 amps wire. Now you have your right hand with your thumb going into the screen, right? That's the direction in which the current flow, and then you curl your fingers as if you're going to grab it, and then you have a field that is like this at that point. So the total field is given by summing up those two quantities. So B is equal B20 plus B5. So you know the direction is pretty much going up, and then the rest is just to plug the equations of a magnetic field created by this long carrying wire. So mu naught times the current divided by 2 pi times distance. The distance is half, right? Half. 0.1 plus mu naught times 5 divided by 2 pi, and also the same distance, and then you can solve the problem. And mu naught is a constant. Now it's the same problem. Solenoid. The solenoid is something like this. It has a bunch of wire, and like those you saw in the lab. And the solenoid creates a field inside the tube that is given by mu naught and I. I is the current that goes in each one of these loops, and N is the density of loops, which means the number of loops divided by the distance or the size of the solenoid, basically. So that's it. And to find the direction of field, you have to apply your right hand rule. Oh, excuse me. So, for instance, if the current goes downward like this, which means every single loop goes downward in the outer part of this solenoid, then the field is like that. It goes like that, right? This is the direction of the field, and then it loops around, and it goes like that. Okay. Excuse me. Okay, so let's tackle the problem. We have an ideal solenoid that is 34 centimeters long. Please change to meters. Carry a current of 2 amps. The magnitude of magnetic field generated at the center is equal to 9 microtesla. How many turns? So then you just apply the equation. So B, which is 9 times 10 to minus 3 Tesla, is equal mu naught times the number of turns divided by the distance, which is the size of a solenoid, times the current, and then we can find N. An ideal solenoid has, now the N is given. Now the N is being given. And the diameter, so diameter is not the size, diameter is given, 4 centimeters. So just go quickly and change that to meters. And it has a size, so D, as we use up there, right? The length of the solenoid is 50 centimeters. So let's convert that to meters. The winding carrying a current in the sense shown in the figure, the current produces a magnetic field, B 4.1 microtesla. At the center, what is the current in the solenoid winding? So you want to find B, is the same idea. Just for exercise, the magnetic field is like that, goes inside the solenoid like that. But you take B is equal to mu naught and I, so 4.1 times 10 to minus 3 is equal to 4 pi times 10 to minus 7 times 470 divided by 0.5, which is D, times the current, and then you can find the current. So this diameter is here just to confuse you. And that's it. So let me know if you need any help. But review the homework, review the problems I gave in class in magnetism. In case you cannot solve, just send me an email. I can do a quick video for you if I have the time. Thank you.